We're going to talk about pH now as it relates to acid and base ionization. Some people may have been bothered in the past presentation where water was sometimes acting like an acid and donating hydrogen ions to things, and sometimes it was acting like a base and accepting hydrogen ions from other things. And as it turns out, water molecules are continually exchanging hydrogen ions, so they can donate hydrogen ions to each other. So water is continually ionizing to produce hydronium and hydroxide. So one water molecule can basically give its hydrogen to a neighboring water molecule, creating an equivalent amount of hydronium and hydroxide. And I want to emphasize here that it's an equivalent amount if it's just pure distilled water. So what does that mean in terms of the concentrations that we observe? For normal water at 25 degrees Celsius, the concentration of hydronium ion should be 1 times 10 to the minus 7 moles per liter. And since every time one hydronium ion is created, a hydroxide ion is created at the same time, so that concentration should be equivalent. Sometimes rather than using these really small concentrations, we'll use a logarithmic factor that relates the concentrations, and we call that the pH. So if I take the negative log of my hydronium ion concentration, I get the pH, and in this case it's 7. And we don't talk about it much, but we could take the negative log of the hydroxide ion concentration and have a pOH of 7. And you may have recalled from other classes that this is what we consider a neutral pH, and that pHs greater than 7 are considered basic or alkaline, and that pHs less than 7 are considered acidic. One thing about the hydronium and hydroxide ion concentrations is that when they're multiplied together, we always get 1 times 10 to the minus 14. And if we have our pHs, the sum of the pH and pOH is always 14, at least at 25 degrees Celsius. Okay, so we can go the other direction. If we had had pH or pOH, the mathematical function that takes us in the reverse direction to get us back to concentration is the power of 10. So one of our exponential functions, the exponent of 10 here. So 10 to the minus pH will give me my hydronium ion concentration, and likewise 10 to the minus pOH gives me my hydroxide ion concentration. And once again, I'm reusing one of my slides here. So just to hit home here, the hydronium times hydroxide is 10 to the minus 14, and that pH plus pOH adds up to 14. So I kind of have a diagram that I like to use, that if I have the hydronium, I can take the negative log and get the pH, or if I have the pH, I can take 10 to the minus pH to get to my hydronium ion concentration. If I have the hydroxide ion concentration, I can get to the pOH by taking the negative log, and then vice versa. If I take 10 to the minus pOH, I can get back to my hydroxide ion concentration. Some people are familiar with how to do these things on a calculator, and I kind of have a sketchy bunch of slides here kind of trying to get you to understand how to use your calculator to get back and forth. I've just kind of come up with a random concentration here, 3.8 times 10 to the minus 5 moles per liter. And if I want to turn that into a pH, if I know that's the concentration of my hydronium ion concentration, what I do is I type a negative, and then on this type of calculator, log, so you should see minus log displayed when you do that. Type the numeric portion of the concentration, so in this case 3.8, and then we have to use our scientific notation key, and on this calculator you have to get that through your second function and then get to that EE, so the EE stands for scientific notation for some reason. And then we just type in -5, close our parentheses, and then hit our answer here, and we should get an answer. At least what I had calculated was that this was a pH of 4.42. On a fancier calculator, if we were going to do this, we would first enter negative, and then log, type in 3.8, use our scientific notation key, which again, we have to go second EE, type -5 for the exponent, and then close our parentheses, and then hit enter. And again, the answer is supposed to be 4.42. Okay, if you have kind of a cheap calculator, the type that are on sale right now this time of year, sometimes when you hit the function buttons like log, it doesn't literally type out the word log for you. So these are kind of what I would call my generation calculator. They didn't show you those. But anyways, on this one, you have to put in all the numbers first and then hit log. So on this one, what I would do is I would type in 3.8, get to my scientific notation key, and on this one, it's the EXP key, and then type in -5, and then hit my log key, which will give me a negative number, but what we've just calculated up to this point is the log of the concentration. We want the negative log, so we can toggle that by doing the negative sign again. So if we do that, we'll end up getting our answer. I assume since we do this, we'll hit the equals, and we should again get 4.42 for a pH. Okay, going the other direction, if we have the pH but we want the hydronium ion concentration. So to do this, I have to take the exponential of my, or the power 10 exponent of my pH. So what I do is first type in the 10 to the x function here, and you get there by going second, and then 10 to the x is above the log key. Type in negative to make it a negative pH. Type in whatever the pH value is, close your parentheses if there are any, and then hit equals. And what I got out of this was 6.8 times 10 to the -4 moles per liter. A fancier calculator here. So again, we're playing with the pH of 3.17. I want to get to that 10 to the x key, so second, and then it's usually above the log key. Type in negative to get my negative pH, and then close the parentheses if there are any. Hit equals, and you should again get 6.8 times 10 to the -4 moles per liter. Okay, on the old time calculator here, type in your pH first, but make it negative. So type negative, and then whatever your pH is, hit the shift key to get to the 10 to the x, because we enter our function after we've entered our number. So 10 to the x, and then sometimes some of these calculators will display the value right away after you hit that, but if you don't get a display right away, then maybe hitting the equal key will bring that up. So those are just some kind of general guidelines in terms of how to use three of the more common types of calculators that are floating around in class. Okay, we'll only deal with calculating concentrations and pHs for strong acids and bases. So what we have to remember is that a strong acid or a strong base ionizes 100%. So to calculate the pH of a 0.25 mole per liter hydrochloric acid solution, I want to write out the ionization reaction. And I remind myself that the hydrochloric acid concentration is 0.025 moles per liter. It's going to ionize 100%, so that means that I get an equal amount of hydronium ion. So this will be 0.025 moles per liter hydronium. So we're in the home stretch to calculating our pH. All we do is take the negative log of that. And what I got was a pH of 1.60. Okay, so let's see. If we're working from the other direction and we have the pH, but we want to know the original concentration of our hydrochloric acid solution, we need to work the other way. So I know that the pH is 3.07. In order to get to the concentration, I've got to use the negative log. So negative log, or not the negative log, but 10 to the minus pH, sorry. So I type in 10 to the minus 3.07, and I got 8.5 times 10 to the minus 4 moles per liter. That would mean that since this is a strong acid, it had ionized 100%, so the original concentration would be equal to my hydronium ion concentration. For bases, it works kind of the same, but you have to be on your toes. So I know that these ionize 100%, so if I had a 0.025 mole per liter sodium hydroxide solution, it ionizes 100% to produce 0.025 moles per liter of hydroxide. To get to the pOH, I've got to take the negative log of that concentration, and I got 1.6. So I have to look at this. I want the pH. What I just calculated here was the pOH, and I know that the pH plus the pOH adds up to 14, so the pH of this is 12.4, and that makes sense because I expect pHs greater than 7 to be basic, and this is a base that we're dealing with. If we were going the opposite direction, then we also have to keep on our toes as well. If the pH is 10.07 for a strong base, I would be calculating the hydroxide ion concentration. So pH plus pOH adds up to 14, so that means that the pOH here is 3.93. So if I take 10 to the minus pOH, I get the concentration of hydroxide ion. If I recall that this resulted from a 100% ionization of the sodium hydroxide, the original concentration of my sodium hydroxide solution would be 1.2 times 10 to the minus 4 moles per liter. So that's the basic process of going between concentration and pH. I've got a couple tricky problems for us to try here. You guys are all as smart as can be, so I'm expecting great things out of you. You have to be a little bit careful if you are dealing with an acid that has 2 acidic protons and bases that end in 2 hydroxide ions. So we're going to make an a kind of a assumption here that we have full 100% ionization. So that means that sulfuric acid, when it ionizes in water, will produce 2 moles of hydronium ion, and likewise barium hydroxide would produce 2 moles of hydroxide ion. So what does that mean? If I've got 0.01 moles per liter of sulfuric acid, what does that mean for the concentration of the hydronium ion if the stoichiometry is 1 to 2, as you can see here? So for every 1 mole of sulfuric acid, I get 2 moles of hydronium. And for every 1 mole of barium hydroxide, I'm expecting to get 2 moles of hydroxide ion. So, and just arbitrarily here, I'll have you turn those in for credit. And good luck with these and the other homework that's on Mastering Chem.